Hello, I'm VJ Stroop, an undergrad at the University of Central Florida. I am joined with folks from the University of California, Davis and Ohio State University in our evaluating temperature dependence from experiments and data analysis on lead islands growing on uranium-111. Taking a look first at the image shown on this slide, we can see the raw data on the left and the process data from our algorithm on the right. Epitaxial growth of metal on semiconductor surfaces is currently industry relevant and an important phenomenon in material processing. Shown on the right is a previously studied lead on silicon 111 surface where lead islands were found to have explosive growth. Now listed at the top of this image is a critical coverage of 1.22 monolayers. This only takes into account the left-hand side of this picture where we see a top-down view of the data. On the right-hand side, we have a more realistic demonstration of the data, where it has multiple layers and these islands actually have heights to them. With the heights included, it was found that the lead on silicon 111 had a critical coverage of 1.48 monolayers. For this project, we're interested in the similarity between uranium-111 and that of silicon-111. In the top right is the apparatus used for the experiment. More details on this will be explained by Andrew Kim, the experimentalist, in the next talk. For a summary of the experiment, lead is evaporated onto a uranium-111 surface. Low energy electron microscopy, LEAM, is used for capturing surface morphology. And in this work, we used computer vision to capture the size and growth rates of lead islands from LEAM images. So on the bottom here are 5 sampled images of the LEAM data. On the very right, at time equals 3,270 seconds, we can see a lot of islands there. Going back one step, at time equals 2,870 seconds, we can see those same islands represented, but they're a little bit smaller. Going back even more, they're smaller again at 2,770 seconds. And going back one more, we can see one little speck there in the middle with the naked eye at 2,670 seconds. Now jumping all the way to the left part, at time equals 2,570 seconds, with the naked eye we really don't see anything there. However, when we first started our analysis, we found that at a time way before the human eye could see, there were actually lead islands growing. So with this, we're able to have a more accurate result of the critical coverage. For our algorithm, we mainly used 4 libraries. NumPy for our array arithmetic and data copying, OpenCV for our image manipulation and getting island contours, Matplotlib for plotting our results that will be shown at the end, and SciPy for smoothing those result curves. The left and center image are the raw data, and the right image is the process data from our algorithm. How this algorithm works is that we first take a centered crop of the data as shown on the left. Now the reason for this is because in the early stages of the experiment, the lens of the LEAM camera was damaged. From this damage, along the bottom, there were many false positive islands. So since we were only interested in the growth rate of the islands, we were able to take a center crop and just use a sampled amount of islands to find the growth rate. So after we took our crop, we then divided the crop into many different sections of squares. We called this method chunking. So we would take 28 by 28 squares, and then within each square, we would remove noise and background from the data, as shown on the right. We would then calculate the number of pixels that are considered as lead islands, and from this we were able to find the critical coverage. The reason why we did chunking is because when we were to subtract the noise and background from the image as a whole, from the crop, the edges of the islands were less accurate than when we used the chunking method. The lead flux is calibrated at the beginning and the end of the experiment. As lead is evaporated, the flux does not stay constant during the whole growth, so we do not know the instantaneous flux at any time. We assume that the total lead coverage at the critical point is 4/3 monolayers. The average lead flux from the start to the critical point is estimated as the flux of the midpoint, from which point the flux linearly changes. For our results, we have 4 different temperatures. For each one of these results, on the right-hand side, we will have a left column for the raw data, and on the right-hand column is the process data from the algorithm mentioned earlier. For our highest temperature at 3 degrees Celsius, the number of islands grow until a coverage of around 1.6 monolayers. The total area of islands grow more rapidly before 1.6 model layer coverage than after that point. At -6 degrees Celsius, we can see that the number of islands grow and slowly approach a constant number at around 2.5 model layers. And the total area of islands grow more rapidly before 1.7 model layer coverage than after that point. As a quick note, the raw data has been shown in a different contrast. Taking a look at the middle row, we can see that there's a bright yellow area in which a static computer vision algorithm might detect the yellow area as islands. However, because our algorithm is actually dynamic in that as time progresses, the threshold for what is an island and what is not is adjusted depending on the surrounding area, we are able to more accurately determine what is and what is not an island. For -15 degrees Celsius, the number of islands grow and slowly approach a constant number at around 1.6 model layers. And the total area of islands grow almost linearly with LED coverage. And at our coldest temperature at -24 degrees Celsius, the number of islands grow and slowly approach a constant number at around 1.5 model layers, whereas the total size of the islands grow linearly with the LED coverage. Now we can see with the colder temperatures also that the number of islands plateau more steadily than the higher temperatures. Putting all of our results together and taking into account Theo's theoretical value for the critical point as 4/3 monolayers, we can see the explosive growth of the LED islands. With the plot on the left of the percentage area covered by islands, we can see that at colder temperatures there tends to be more area covered than there are for higher temperatures. We can also see that at -6 degrees, the growth rate tends to be higher than 3 degrees Celsius up until about 1.6 model layers. Then after, it holds true again that the colder temperature grows faster than the hotter temperature. We can also see that -24 degrees Celsius and -15 degrees Celsius tend to have the same growth rate till about 1.7 model layers. Looking at the middle graph, the number of islands, we can see that with lower temperature, there tends to be a lot more islands than there are at higher temperature. Now, the reason why the -24 degrees Celsius, our coldest temperature, does not have more islands indicated than the -15 degrees Celsius is because as our temperature decreases, the islands start to clump together, thus reducing the total number of islands. On the right, the average area of islands, we can see that the higher temperatures tend to have an average area greater than the lower temperature. This is because, as we know, at higher temperature, atoms diffuse more. So, in conclusion, what we have found is that the colder the temperature is, 1, the faster the area growth will be, 2, the more number of islands there will be, and 3, the smaller the islands will be. All of these are similar to that of silicon as previously studied, and these results also show that temperature is a factor that can control the growth of lead islands on uranium-111. Thank you for listening to my talk. If you have any questions, feel free to submit them to the APS platform or email me at vjstroop@knights.ucf.edu, and I'll try to get back to you as soon as I can. Thank you.